So picking up with the chain rule, we're on example 1D. And recall that the chain rule is used when we're taking the derivative of what type of function? Composite functions, yeah. So this was one of the ones in the beginning that we said we could do. You have two terms. If you put parentheses around the layers to help yourself see the layers, that's not a bad deal. So now the derivative of the first term is just 1 minus, and some people miss this on the quiz. What's the derivative of tangent of blob? Secant squared of the blob, and then times, in that term only, the derivative of the blob, which is 2x. Okay? So that 2x is only multiplied by the second term, not both terms. So if you simplify that now, clean it up a little bit, bring the 2x to the front, you get secant squared of x squared again. And you really don't need the parentheses. So we can combine the chain rule now with all the other rules that we've learned before, like multiple terms, power rule, product rule, quotient rule, and all the trig rules. All right, this one here, we don't necessarily need to use the chain rule because it's just a quotient, right? You can ho d high it, and d high would be 0. But if you ever have a question like this with a numeric numerator, it's just a number. It could be any number. It's probably a little bit faster, if not easier, and less likely to make a careless mistake if you bring the entire denominator to the numerator and say it's to a negative power. Now you can use the chain rule, okay? If you do the chain rule now, you have two layers. You have blob to the negative first and the inside blob. So when you take the derivative, you get negative blob to the negative second, and times the derivative of the blob is what? What's the derivative of x plus 1? 1. So when you clean that up, you get negative 1 over the quantity x plus 1 squared. And that would be the same thing you get from the quotient rule. But if you had to take like a second derivative or a third derivative, notice that this line right here is already set back up to take higher order derivatives. Multiply by negative 2, subtract 1. Multiply by negative 3, subtract 1. So on and so forth. So just look to kind of simplify rational functions when you have a single number in the numerator. The chain rule works a little bit faster, a little bit cleaner than the Hody-High rule. All right, d dx of sine squared of 3x. How many layers do you see on this one? Well, maybe it's hard to see them right now. I will tell you this. Whenever you have a trig function or a log function, and it's written in condensed format, okay, it works with log as well, like log cubed of x. That's the same as the natural log of x quantity cubed. You're probably going to want to write those in expanded format to help you see the layers. So I'll go ahead and use flavors here. The first layer, I'll call the purple layer, it's blob squared. Inside the blob squared layer, we have the sine of the blob, and then the innermost layer in beefy brown is 3x. So how many layers do we have there? 3, right? The purple layer, the green layer, the beefy brown layer. So you're going to have 3 factors in your chain rule result. So here they are. The first one first, blob squared becomes 2 blob to the first, and we'll just write down the blob. Remember, you're only taking the derivative of 1 layer at a time. Times, now we're at the green layer, the derivative of sine of blob is cosine of the blob, and then times the derivative of the innermost blob, the derivative of 3x is 3. And so there's the answer. 3 factors from 3 layers, we're done. Now to clean it up a little bit, you could do one of 2 things. You could bring the 2 and the 3 together and call them a 6 times sine of 3x cosine of 3x. That works great. Or, does anyone recognize something you could do with this? That's something y'all are supposed to know. Remember, sine of 2x is equal to 2 sine x cosine x. That's the double angle identity for sine. And it doesn't always have to be x. It could be blob. So 2 sine of blob cosine of blob is equal to sine of twice the blob. So 2 sine of 3x cosine of 3x can also be written as sine of what? 6x. And that will take care of those, and then we would just have a 3 in the front. So either one of those are correct. The bottom one, though, I like that better for a multiple choice answer because it's less typing for me. I also like it later on when we're going to be using these things because it's only one variable factor to work with instead of 2, a sine and a cosine. So keep that in mind. If you haven't committed this to memory, commit it to memory now. Get on the bandwagon. And while we're at it, cosine of 2x is the one that looks a lot like Papa Pig. That one's cosine squared minus sine squared. That's a minus sign. Go away. Get out of here. All right, minus. There we go. All right, so triple layer. Rewriting, expanding it, and putting parentheses around things to show layers, especially in the beginning, can be very, very helpful. It could be very, very helpful for who? Bear with me today, guys. What am I trying to say? It could be very helpful for you. Thank you. All right, letter G. The bottom row here gets a little more interesting. We have x times secant of the blob. So when you walk up to the problem, what's the first rule that you're going to be using? The product rule. So I'm going to add grouping symbols. X is one factor, secant of blob is the other factor. So here we go with the product rule. The derivative of x is 1. Now you don't have to write 1 because it's the identity element of multiplication. I like to write it for inventory purposes. I know that I took the derivative and not just forgot to do something. Times the second goes along for the ride. Secant of x squared plus x plus 1. Okay, so there's the first one. And then plus, now x goes along for the ride, times the derivative of secant of blob. Bless you. What's the derivative of secant of blob? Secant blob, tangent blob. Secant blob, same blob, times tangent of blob. And now, since I said blob, I have an innermost function. Now we're going to multiply times the derivative of the blob, which is what? 2x plus 1. Now notice how I wrote it there at the end. That would be losing it at the very end. What should 2x plus 1 be inside of? Parentheses. Otherwise, that last term is only multiplied by the 2x, and the plus 1 becomes its own little term when it's not. Okay? So there's the answer. That's the final answer. You can't really do much with that, but you could factor out a secant of blob if you wanted to. I'm not going to clean that up, because right now we're just kind of practicing the derivative part. All right, any questions on that one? It only became a chain rule in the second term when we took the derivative of the second factor. All right, letter H. The derivative with respect to m of secant of 4 minus cosine cubed of 5m. We're going to want to do a little bit of rewriting on this one for inventory purposes. So here's what it would look like. The derivative with respect to m. We're going to have a secant function on the outside. So I'll switch flavors here. The next layer is going to be 4 minus blob cubed. See that? 4 minus blob cubed. That's cosine cubed. And then inside that second term now we have cosine of blob. And inside there we have the blobbiest of blobs. I'll use red, the 5m. Now that you see all the layers in wonderful colors, you can work from the outside in. So first things first, the outer layer is secant, and the derivative of secant, as we've already seen, is secant blob, tangent blob. So kind of not the fun one to write, because you've got to write it twice. 4 minus cosine cubed of 5m, secant times tangent of the same blob, 4 minus cosine cubed of 5m. So there, that takes care of the secant layer. And now you go inside one layer and you spot the purple layer. So I'm going to put parentheses, which is a good idea because, remember, you're going to be multiplying by factors and sometimes factor groups. And those factor groups can have multiple terms. So in the purple layer, what's the derivative of 4? 0. I'm going to go ahead and write down 0 as a placeholder, minus blob cubed. So that's going to be minus 3 blob squared. And we just write the blob down. Times, only in that second term now do we have more things to multiply by. So we're still kind of inside there. Times the derivative of cosine of blob, which is what? Negative sine of the blob. And then times, on that piece only, the derivative of the 5m, which is 5. And now we can come back and close that purple layer that we opened way over there. You have to use the chain rule as you get to it. In other words, as you work from left to right or outside in, you have to totally unpack all the boxes before you go on to the next term. Now, because that right there is a 0, it's not its own separate non-trivial term, that kind of makes this problem a little bit nicer. But otherwise, we would still have 2 terms there. With that gone, you can actually start combining a lot of things here. Not a lot of things, but you could say that's a -3 times a -1 times a 5. What does that give you? That gives you a +15. You could bring that way out to the front. So that's +15 times, I'm just going to use notability right here and copy and paste that down. So that doesn't really change. And then what's left in the back end there? We're going to have a cosine squared of a 5m times a sine of a 5m. And that is about as simplified as that gets. And it's still pretty ugly. Okay? If this had not been a 0 right here, then all you would get to do to simplify it is take this entire thing and distribute it to both terms. But we didn't have to worry about that because it was a 0. But the point of this problem is not necessarily to simplify. You're not going to ever have to work with anything this grotesque. The only reason we're doing this grotesquely now is because you're stopping after the derivative. You're learning how to take the derivative. And if you can keep track of a problem like this, with all the grouping symbols in the right place, you'll have the chain rule down. All right, so in the last one here, we're back to regular old x. When you walk up to the problem, what do you see? Do you see a hoodie high? I don't even see that yet because I only see these walls right here. I see hello blob squared. So this is a chain rule first with a quotient rule inside of it. So working from the outside in, blob squared becomes 2 blob to the first. And the blob is just 3x minus 1 over x squared plus 3 times. Now we go inside, and we're saying, oh, wow, we hit the jackpot. Inside these walls that we couldn't see in previously, we have a quotient, our lucky day. So now we're going to multiply by the ho d high rule. So ho d high, remember you start with a ho, you end with a ho. D high is 3 minus high. D ho is 2x, all over ho ho or ho squared. All right, let's see what we could do with this. We could simplify this a little teensy-weensy bit. If you multiply straight across, you can call that 2 over 1. What's your new denominator going to be? If you multiply across in the denominator, yeah, you'll have 3 of them. You'll have cubed. So that takes care of the denominator. Now you're going to have a 2 times the quantity 3x minus 1. Does anything inside here factor out? Do we have a common factor in those 2 terms? No, not really. So I'm just going to write it as parentheses 3 times x squared plus 3 minus 2x times 3x minus 1. Close, close. And that's about as much as I'm going to simplify that one. You could, at this point, expand all of this inside there and collect like terms, but we'll save that for another day. We're practicing the derivatives right now. All right, any questions on those? So far, so good? Chain rule? Chain rule. All right, well, that takes care of example 1. That was a long example 1. It spanned 2 days. We're on example 2 now. Find all the x values, not y values, just the x values, on the graph of this dude for which the derivative is equal to 0 and for which the derivative is undefined. Okay, well, apparently, if I needed to find out where the derivative is 0 and undefined, I need the derivative function. So let's go ahead and do that. I'm going to rewrite it first. Anytime you have a radical, you're going to want to rewrite it as a rational exponent. So we're going to have x squared minus 1 squared all to the 1/3 power. So the way I have it written right now, how many layers do we have in our function? 3, right? You got the blob to the 1/3, the blob squared, and then the blob itself, which is x squared minus 1. Can we do anything there to eliminate one of the layers and therefore eliminate one of the links in the chain, making it less likely to make a careless mistake? Yeah, you can actually combine these. You can multiply 2 by a third, and that simplifies it. And you could do that right away. So if you could do that in the first step, just go straight from there to there, that's great. But if you can eliminate a layer, you eliminate a lot of work and possible mistakes. So now there's only 2 layers, so we'll have 2 links in our chain. A very short chain. I wouldn't use it for the dog in the backyard. That's cruelty to animals. They need more room to run. All right, so working from the outside in, blob to the 2/3 becomes what? Absolutely, to the negative 1/3. You get good with fractions. Times the derivative of the next layer is what? 2x. And we're done with the calculus. It's always fleeting. It doesn't last very long. Now, because we're going to use this, and here's really the benefit for cleaning it up. We want to use it. We want to figure out where it's equal to 0 and where it's undefined. And so we want to get rid of negative exponents, and you want to get rid of fractional exponents. So this is just one big term, so I'm going to go ahead and build my shelf. What goes in the numerator? A 4x. Good. You got a 2 and a 2x. That gives you a 4x. And in the denominator, you have the 3 factor, and then the other factor goes back to the denominator and goes underneath the radical, x squared minus 1. Okay, so now we're going to use this twice. So kind of like do a little fork in the road. The first thing you want to do is see where f prime of x equals 0. Anytime you are solving an equation, you have to show the equation you're solving. All right, in this case, we're setting the whole thing equal to 0. Now, because it's a single fraction is equal to 0 when the what is equal to 0? Just the numerator, yeah. So once you say f of x equals 0, you're going to pretty much earn a check on any kind of short answer. But then that happens when 4x is equal to 0. And now you can solve that, you get x equals 0. So because the derivative there was 0, what type of tangent line do we have there? Yeah, horizontal tangent line. Bless you. And now we'll kind of come over here on the other fork. We want to know where the derivative does not exist. So that's essentially going to be, we have a cube root. Are we allowed to have negatives under a cube root? Yeah. So the only thing we're trying to avoid now, because there's really only 3 situations. You can't take square roots, 4th roots of negatives, can't divide by 0, and can't take logs of anything but positives. We don't have logs and we don't have even roots. So the only peril is division by 0. So what you're essentially going to do now is say f prime equals dne. That shows the equation you're solving when the denominator is 0. So now you'll just take the denominator and set it equal to 0. And you'll be finding the values that give division by 0. These will be the values where the function is not differentiable. So how do you solve a little equation like this? Divide through by 3, cube both sides. You end up with x squared minus 1 equals what? Still get 0. Yeah, so if you want to kind of trim off some of the steps in your head, that's fine. You can solve that 2 ways. You can isolate the x squared and extract the square roots, or you could factor it. Or you can just look at it and tell me what the solutions are. What are they? Good. Yeah, so you don't even have to show the work. However you want to get it, there's 2 solutions. And those are going to be what type of tangent line? Vertical. How do we know they're vertical? They make the denominator 0, and what do they do in the numerator? Something other than 0. Good. Remember, non-zero over 0 is some type of infinity. And because we're talking about f prime, you're talking about slopes being infinite. These are going to be vertical tangent lines. Vertical tangent lines. Or cusps. Because remember, they can look something like this. It goes vertical there and then comes back out of it. Or it could do something like this. It goes vertical and then it comes back out of it like that. So either one of those. That's what's going on there. Yes, we're going to come back and do that at the end. I want to make one more point before we get back to cusp alert. Horizontal tangent lines, that's going to look either like this, or it could be something like x cubed or negative x cubed, where it's just a stationary point and we're increasing through it. So these are going to be very important to us later on. We're going to be setting out on our own to figure out where the derivative is 0 and where the derivative is undefined, because these end up being what we call critical values. So I'll throw that word out there early. It's a vocabulary word. A critical value is a place where the derivative is 0 or undefined, and they're very special. Now, if we retreat all the way back up to the top, notice your original function has a 2/3 as an exponent. 2/3 is less than 1, right? So when you use the power rule and you subtract 1 from a number that's less than 1, what type of number are you going to get? You're going to get a negative number every time, which is going to throw that quantity from the numerator to the denominator. So here you go. Anytime you have a fractional exponent, that's between 0 and 1. I'll just do it like this. You're going to be on what, Colin? Cusp alert, cusp alert, cusp alert. Red flag goes off, right? Cusp alert. That's one word, it's a portmanteau. Cusp alert or a vert alert. Vert alert, vert alert, vert alert. So you're going to anticipate values that are in the domain of the function. The function is going to be continuous there, but they're not in the domain of the derivative. They're not going to be differentiable there. And they're going to manifest like that, bless you, or it could be a cusp opening down. But those are going to be important values to us, because notice they could possibly be local maximums or local minimums if you look at the cusp versions of it. All right. Any questions on number 2? It's kind of a neat little question right there. All right. Example 3, kind of taking one step further. F of x is equal to 1 over 1 minus 2x quantity cubed. So to find the domain of f of x. So we did a lot of this in pre-calc. What are the 3 things we're trying to avoid for non-piecewise functions, things that affect the domain? Zeros on the denominator. We got that risk here, so we got to look out for that. What? Yeah, no negative logs or 0 for logs, right? Just positive numbers behind logs, and very good. And we have no radicals here or fractional exponents. So the only thing we need to avoid here is division by 0. So 1 minus 2x quantity cubed cannot equal 0. If you take the cube root of both sides, 1 minus 2x cannot be 0, and 1 cannot equal 2x, and therefore x cannot equal 1/2. So if you remember, we write the domain kind of in a fancy way. We say the domain with the subscript of f, that's the name. It's the set of all x's such that x is not equal to 1/2. So recalling from pre-cal then, the graph lives to the left of 1/2, lives to the right of 1/2, but not at 1/2. That's going to be a discontinuity, for sure, for sure. What type is it? It is a vertical asymptote. Again, how do you know? Yeah, non-zero over 0 means plus or minus infinity. And when you're not talking about the slopes, but you're talking about the y values, that's because there's a vertical asymptote. So if you got 0 over 0, it would be a hole. So we know then that f has a vertical asymptote at x equals 1/2. Just for kicks and giggles, does it have any end behavior asymptotes? How do we analyze end behavior asymptotes? What limit do we take? Infinity, good, or negative infinity. So if the top is always staying a 1 and the bottom is effectively a cubic function, it's going to 0. Yeah. So we do also have, we're not trying to sketch the graph here. That's a whole section later on called 3.6. But it does have a horizontal asymptote at y equals 0. It's an end behavior asymptote. All right, part B, this is what it's leading up to. Show that the slope of every tangent line is positive. Show that the slope of every tangent line is positive. How are we going to do that? What function do we have that gives us information about tangent lines? The derivative, yeah. So we need to find the derivative. So let me rewrite the function down here. F of x is 1 over 1 minus 2x cubed. We could use the Hody-High rule here, yeah? Or the chain rule. Very good. So let me rewrite that as 1 minus 2x to the negative third. And now it comes a little bit quicker with less risk of an error. F prime of x is Negative 3 blob to the negative fourth times what? Negative 2. All right, now we're trying to use f prime. If we needed f double prime, we could go ahead and take another derivative right there. But we're going to use f prime, because y'all said that's the one that deals with the slopes of tangent lines. So this becomes a 6 over 1 minus 2x to the fourth. Now what? What was our mission here? We have to show that all slopes are positive. So it's the same task as trying to show that the derivative is what? Greater than 0. Where? Everywhere. Is it? Let's see. The numerator is always a what? Positive 6. Good. Not just a 6, but a positive 6. And the denominator can be negative inside the parentheses, but to the fourth power, it's always positive. So here's all you have to say. F prime of x is greater than 0 for all x, period? Or for all x except what? This is where students tend to lose points. Yeah. I had you find the domain up here, and remember, 1/2 is not in the domain of the function. So this is greater than 0 for all x not equal to 1/2. If you just said that it's greater than 0 for all x, guess what? You're wrong. You lose a point. And a lot of the times in the questions when they're given to you, they don't just ask you on part A to find the domain. That's something that you have to consider on your own, and be careful when you say some blanket generalization for all values. Now, because the slopes are always positive over the domain, we can now say, so f of x is doing what? What is the graph doing from left to right if its slopes are always positive? Increasing. And when something is only increasing or only decreasing on an interval, we say it is monotonic, or the other word, I heard it as well, strictly. They're used interchangeably. F is monotonic or strictly increasing over its domain. Over its domain. That's pretty cool. So we don't even really know what the graph looks like, but we know a bunch of information about the graphical features just by doing the calculus analysis. And that's what the last part says. What conclusion can you draw about f of x from this? And that's it. F of x is monotonically strictly increasing. You do have to say over its domain, or again say for all x not equal to 1/2. Since we've already found the domain, we can just kind of refer back to it. All right, that's actually a proof. You just proved that that function is going uphill everywhere by doing a calculus proof. All right, any questions then on number 3, or any comments? Y'all like f of x? There's so many of them. Yeah, so many. We should use different names, like g of x, or h of x. Or what? Wife? Or y? Why? You like that a lot if you're calling it your wife, right? Why? In each of the following, find dy dx, and then simplify dy dx by factoring out least powers. I think we've done this year already, haven't we, factoring out least powers? This is factoring out when you have fractional exponents and not integer exponents. It's a lot more fun. Okay, but first things first, we got to find dy dx. All right, what do you want to do with this function before we even start that? Rewrite it. Good. So you'll have y equals x squared. I'll put that in parentheses, times the quantity 1 minus x squared to the 1/2 power. So what rule out of the box is this going to be? Product, right? If the first factor is f and the second factor is g, Tyler, what's the product rule? Okay, that'll work. Yeah, f prime g plus f g prime or g prime f. It's commutative. All right, very good. So here we go. dy dx is the derivative of the left. I take the derivative of the first one first. So the derivative of x squared is 2x. Times the second one goes along for the ride. Plus x squared goes along for the ride times the derivative of the second factor. That's going to require the what rule? Chain rule. So here we go. 1/2 blob to the negative 1/2 power times the chain rule, the derivative of 1 minus x squared, which is negative 2x, 0 minus 2x. I was kind of hoping Mr. Falcone would stay for the factoring out of the least powers. I doubt he's ever seen that done before. Maybe that's why he left. He got scared. He's a math teacher. He taught Algebra 1 before he became an administrator. Okay, so there you go. Let's go ahead and do a little bit of house cleaning here. 2x, 1 minus x squared to the 1/2. Now, when you're factoring out least powers, you want to leave those quantities to fractional powers instead of putting them back under radicals. A little bit easier. The second term is really where a lot of the cleanup is going to happen. This 1/2 and that 2 divide out, and we're left with a negative still in that last term right there. And then an x times an x squared is an x cubed times the 1 minus x squared to the negative 1/2. So because in the previous example we liked having a single fraction so that we could set the numerator equals 0 and the denominator equals 0, that's why we do this. This is two terms. We want to get it into one term, so we want to factor it. And that's where the least powers comes in. It's the quickest, fastest way to do that. So I don't see any number other than 1 or negative 1, so I'm not going to worry about that. But we do have at least how many x's? We have at least one x, x to the first, x cubed, 1 is smaller. And then on the other piece, 1 minus x squared, which of those exponents is smaller? Negative 1/2. So we'll factor out the smaller of the two. So this is not least powers, but the lesser powers. And then for some reason, I always feel inclined after we do that to put a beefy brown bracket, the beefiest of all brackets. All right, so here we go. What are we left with in the first term? When we take the x away from the 2x, we're left with a 2. And then here's where we have to really be careful. We are dividing out a 1 minus x squared to the negative 1/2 from a 1 minus x squared to the 1/2. So we're really subtracting the exponents, right? That's what you're doing. Because it's like having this divided by that. So it's 1/2 minus negative 1/2, which becomes 1. All right? So you don't even have to put a 1, but there is a 1 there. And you could quickly test by redistributing. When you multiply this times that, you're going to add the exponents. Negative 1/2 plus 1 gets you back to positive 1/2. And then in the next one, we pull out an x from an x cubed. What's 3 minus 1? 2. Y'all do that pretty naturally. And then we take the entire factor away to the negative 1/2. So that's all that's left inside the beefy brown brackets. Now one more step, and I think we'll have it ready to go for fully factored version. Inside the beefy brackets now, since it's to the first power, you don't really need it there. You're going to want to distribute completely. So 2 times 1 is 2, and then we're going to be left with minus 2x squared minus the other x squared. And now I'm ready to go to my final answer. In the numerator, we're going to have an x times a 2 minus 3x squared. And in the denominator, we're going to have a square root of 1 minus x squared. And that right there is the cleaned up, fully factored version of that function. Okay? So factoring out the least powers is the quickest and fastest and most efficient way to get back to something like that. And now if we wanted to, now we could set the numerator equal to 0. Now we could set the denominator equal to 0. And things will go a little bit faster for us. All right. I'm going to go ahead and let you do B on your own. And I'm going to leave the recording going. So if you're watching the recording at home, do it on your own. Don't even hit pause. Go. Go. I'm going to be doing it in the background so you can kind of look up if you want validation or just keep in your own math zone.
Good morning, unicorns. Happy Tuesday. Keep the day positive. If you guys please rise for the Pledge of Allegiance. I pledge allegiance
to the flag of the United States of America, to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Texas flag, pledge allegiance to the Texas, one state, under God, one and indivisible.
Thank you. As we start our day, continue our day, here's the weather update from the Weather Channel. Today is going to be a high of 75 with a wind speed of 15 to 25 miles per hour.
Seriously? A weather report on the announcements?
Buckle up as we weather coming in. And I'm going to give a shout out to Trick T. So have a great day. Here's Trick.
Thank you, students. Just a reminder, tomorrow is the PSAT. If you're a sophomore or junior, you will be taking it. Please make sure you know your address, your English teacher, and period, your ID number, and please make sure you bring your calculators. We do not have enough calculators for everybody. Also, today is Tuesday. Today's feature food group is fruits. Many fruits are low in calories and rich in vitamin C, which will boost your immune system. Just a reminder, ASVAB sign-up is available until the end of C lunch. Get your passes in the College and Career Center. French Club meeting after school tomorrow in room 227. You don't have to be in the French Club, just be interested in French culture. French snacks will be provided. Also, today is the final day to vote for homecoming court. Winners will be announced Wednesday afternoon. Juniors will have a class meeting to discuss homecoming hall decorations this Wednesday after school in Mr. Bowen's room. Sophomores will have a class meeting in Ms. Walker's room Thursday before school. And pink out shirts will be on sale today during all lunches. We only have larges and extra larges remaining. The floral design class is having a mum-making party on October 17th from 6 to 8. And
I factored out a 1/3 as well, because you're not only factoring out the smaller of the two exponents, but you're factoring out the smaller of the number pieces too. So when you factor out a 1/3 from something that's not there, remember you're still dividing out. So 1 divided by 1/3 is the same as multiplying by 3. So 1/3 times that 3 puts us back at the 1. That way you don't end up with a complex fraction at the end. But if you didn't do that, you could then, at the very end, multiply by 3 over 3, and it'll divide out in the top and reintroduce itself into the bottom. This right here inside the brackets, I just distributed 3x squared minus 2x squared is 1x squared, plus 3 times 4 is 12. It's to the first power, so it doesn't really need to be there. So that's it. Did y'all get that? Or you see how to get that? 2x squared. When I take this thing out right here, I'm left, and the 1/3, I'm left with a negative x times 2x. That 2x came from the chain rule. It's the derivative of x squared plus 4. So that 2x times that negative 1 is negative 2x squared. So that's where that came from. So they're kind of fun. You don't really do a lot of these in Algebra 2 with fractional powers or even fractional numbers. So to be able to practice them here, it's kind of a nice little technique. So just remember, it's the thing that you're factoring out is the thing that you're dividing out. So what you started with divided by what you factored out gives you what's left. Okay? And I think that's where we'll stop for today. And we'll pick up with example 5 tomorrow. All right? Well, not tomorrow. I meant to say Thursday, because I won't see y'all tomorrow. Y'all will be in the library. So have a good time in the library. Hope you read lots of books.